Okay, hello. I'm Michael Ekstrand, as I said earlier, an assistant professor at Boise State University, where I co-lead the People and Information Research team with Dr. Soleil Pera. We do a variety of things around recommender systems, information retrieval, human-computer interaction, generally centered around building better tools to help people meet their information needs. So, get the slide advancing here. And so the central question of my research overall is, how do we make recommender systems good for the people that they affect? Now, there's a lot of questions around what is good, how do we measure good, what people are we caring about, etc. But broadly speaking, this is the central goal of what I'm trying to do in my research agenda. So in support of that, I'm going to talk about a few different things. I'm going to talk some about just a little bit of background. I'm not going to go into a lot of background on the details of what recommender systems are, how they work. I expect most of you are already pretty familiar with that. Some work we've done on building tools and instrumentation, some problems with evaluation that we've been thinking about. And then some research on recommender response to users, how recommendations operate in the broader context. So background, I want to start with just a little bit of philosophical foundation. So I want to make recommender systems good for people, but my understanding of what that means and of the central questions involved in such an agenda are very heavily influenced by the work of Ursula Franklin and her lectures and book, The Real World of Technology. And there's a lot of really good material in there. I think it's great reading for basically anybody involved in building technology in some way or another. But one of the particular insights that I take from it is that technology is not just about artifacts. It's easy for us to think about technology in terms of the things that we build. But Franklin encourages us to step back and think about technology in terms of process. Technology is a means for organizing human activity. And so if we want to understand what a technology is doing, what impact it is having on people, we need to look at the process that it induces and the process that involves around it. How people work with it, around it, in spite of it, etc. And that's where we see a lot of the impact of a technology come up. And then also the fact that it arose from a process. The internet was not, we didn't just go find the internet in a mine somewhere. We built it. We made decisions about how it would be designed. We could have made other decisions. So thinking about the decisions that go into the technologies that we have, the technologies that we build, and thinking of imagining what other decisions might be possible and how we might be able to go about seeing whether what we've built, what we're building, is really the best way to go about advancing human welfare. So, with that in mind, I also want to think a little bit about who the stakeholders are in a recommender system. So oftentimes we focus in terms of measuring the user satisfaction, or we measure the recommender's ability to produce business value, such as conversion rates, or we do offline evaluations that are intended to correlate with some measure in that space. But there's quite a few different stakeholders that have a role to play in recommendation. And if we think about something like book recommendation, where some of the stakeholders are perhaps a little more distinct than they are in some other domains, we have the users themselves. We have the users themselves, and they get the recommendations, they act on the recommendations, they read some books. We have the bookseller who is trying to make money selling books. We have the shareholders who want the bookseller to make money selling books. We have the author who wants their book to get noticed, read, and bought. The publisher wants their author's books to get read and bought, but they have a whole portfolio of authors. And then finally we have society, or the broader community, and the fact that the books that I read affect the way I understand the world around me. They affect the way I communicate with my neighbors, the way they can affect how I affect the world around me. And to what role does recommendation play? What is the outcome of recommendation as far as the kinds of citizens that people who take recommendations turn out to be. There's also the question of who all of these are involved in the design process. How many different stakeholder voices do we have when we're building, when we're evaluating a recommender system? Then, so we've got these users, or we have these different stakeholders. A lot of our focus in recommendation is often on understanding the users. Where does that data come from? Broadly speaking, there are two major categories of data. One is behavioral data, where we look at what the users do, and the other is explicit data where we ask the users to provide some explicit inputs. And so when we look at what they do, we have implicit feedback, clicks, purchases, things like that. We have behavioral A/B testing where we give users recommendations and we see which recommender induces users to buy more. We have our explicit feedback, our ratings, our thumbs up. We have user surveys, and then we have the possibility of doing things like focus groups to understand what users might want from a future product. We also have a set of questions about what the impact of these recommendations are on a variety of groups, on users. So the impact of the whole recommendation cycle on users, on data and algorithms, because as we provide recommendations to users, users act on those recommendations, they take actions which feed into the next iteration of the recommendations that we're going to be producing. How does the recommender's view of the world, how does the recommender's output change over the course of that kind of a feedback loop? And then what kinds of changes do these induce in society? What is the impact of the recommendation system on the broader societal structures that it interacts with, particularly over time? So, with all that in mind, we've done a fair amount of work, and I did a lot of the initial work on this during my PhD to build a set of tools for supporting recommendation experiments. And this is the LensKit toolkit, which is an open source toolkit that lets us build, research, and learn about recommender systems. It lets us build, it's useful for building recommender systems at a modest scale. Our goal is that if you can still fit on one or maybe two web servers, LensKit can provide you recommendations. We're not going to handle Netflix or Amazon, but there's a lot you could do on a smaller scale that we can handle quite well. So you can use it for prototyping a new recommender application. You can use it for research. It's algorithms and evaluation tools allow you to take existing results, replicate and validate them, allow you to use our implementations of existing collaborative filtering algorithms as baselines in new experiments, or as algorithms in new user-facing recommender experiments that maybe want to work with existing algorithms. You can also translate the building and the researching are not disconnected. So you can take the exact same algorithm code, translate it from the offline setting into the online setting, and it interacts well with being deployed as a web application. And then it's all open source code so that students can learn using it. We use it to support online education. We use it to support in-class education. LensKit is behind at least 3 user-facing web services that I know of. The Movie Lens service runs which this slide is slightly out of date. It's now at about 4,500 unique users a month last I looked. It does movie recommendations. The Book Lens book recommender is integrated with the card catalogs of the Twin Cities metro area public libraries and is collecting ratings and providing book recommendation in the public library setting. Also, the Confer system that MIT runs, it's been used at CHI and CSCW and a few other conferences for recommending sessions to go to at the conference, recommending people to connect to. That's using LensKit under the hood. And then we use it in education. The Coursera MOOC on recommender systems in its first 2 incarnations has had over 1,000 students doing the programming assignments with LensKit. We're also using it in class, and it's used in a number of research papers. So that's our software that we've been building, maintaining. Then use that for a bunch of things. The first set of research results I want to talk about are some things we've been doing in evaluation, looking at some problems with where IR evaluation techniques break down when we apply them to recommender systems in some pretty annoying ways. So basically, recommender systems violate the assumption, a lot of the assumptions of offline evaluation. Some of this is well known, some of this is not as well documented. And so how bad is this? Just to rehearse just a little bit, we have an offline evaluation. We've got our data. We split it into trained data and test data, train the recommender on the test data, produce some recommendations, compare them, we trained it on the trained data. Funny story, LensKit's integration test one time caught a bug when my accuracy improved by like 40%. And I went to go dive and figure out why, and it turned out that I was training the recommender on the test data. I had a typo. Fortunately, we caught this bug with testing and didn't put it in production. Train the recommender on the test data, compare the recommendation, or excuse me, the train data, compare the recommendations with the test data. And then we use standard machine learning and information retrieval metrics such as precision, recall, mean reciprocal rank, mean average precision, etc. to measure the effectiveness. So one of the problems, to understand one of the problems, we need to think a little bit about some of the inputs of the recommender. So the recommender, when we're going to recommend items for a user, we have a candidate set, which are some items that we might recommend from. Often the candidate set by default is every item the user hasn't rated, which in an evaluation is every item that's not in, that is not in the user's set of training ratings. So basically recommend anything to the user. But we can think of the candidate set as being broken into two parts. We have the test set, which is the set of items that the users rated or purchased. And we have the decoy set, which is the set of items that are not in that set. And basically the recommender is a classifier trying to separate test items from decoys. Is one way to think about the problem. So, the problem arises because we are missing an incredible amount of data in basically all of our recommender system evaluations. Suppose I have a data set that consists of movies I've watched. And we do a split, and I get back these 5 recommendations. And we know from the data set that I have watched The Iron Giant and Frozen. Now, we do not have any record of me watching Zootopia. So we assume that it's not relevant, and we give this list a mean reciprocal rank of 0.5 and average precision of 0.417. Now, there's actually those 3 possibilities for Zootopia. I don't like it. I do, but the data doesn't know. Maybe we're dealing with Netflix data and I watched it on Amazon Prime. Or 3, I do, but I don't know about it yet. So, a lot of the information retrieval metrics and machine learning metrics assume that we have something that we can treat as a fully coded corpus. There's some useful tools in information retrieval to get a close to fully coded corpus from a not fully coded corpus, but they assume that we know that we have a good idea of whether all of these are relevant or not. But we don't have that in recommender systems, and further, we don't have a good way to get that good idea. So, in information retrieval, there's a few different solutions. So I went with a student to go look and see, okay, what of the known information retrieval techniques that we can find might apply to recommender systems? And unfortunately, the situation didn't come out very well, as near as we could tell. So the one that works is rank effectiveness. So rank effectiveness says that candidate set is only going to consist of rated items, and we're going to look and see whether the recommender puts them in the same order as the user's preference. This works if we have rating data or if we have explicit negatives. Basically, some way where the user where we can explicitly obtain the user likes A more than B. If we have that, we can do rank effectiveness. Works fine. But if we look at techniques such as pooling that's been used in the Trek competitions to expand the set of relevance judgments. Basically, the idea is you take a bunch of search engines or retrieval engines, get all of their results, hand code all of those, and assume that if none of our 50 to 100 engines return the result, then it's probably not relevant. But this uses human expert judges, and you have some objective notion of query relevance. In a recommendation setting, the only real judge of whether a recommendation is relevant is the user themselves. We don't have any objective notion of relevance. Similarly, there's also the idea of relevance inference, where you take known expert judgments and then you use those as a basis for inferring the relevance of other documents to a candidate set. But here the problem is that it's basically begging the question when we try to do it for recommender evaluation. If I have a relevance inference engine that, given a user's ratings, can tell me other things they like, that's an awful lot like a recommender. And if we're evaluating a recommender by its ability to match another recommender and not by its ability to actually predict user behavior, we're not really evaluating its effectiveness, I don't think. At least the HCI person in me says we aren't. So we've got a variety of techniques that don't work as well over in the recommender system space as they do in the information retrieval space. So Now, why is this so much of a problem? Well, if I would like Zootopia, that first recommendation, but I haven't seen it yet, then it's likely a really good recommendation. Not only is it a really good recommendation, but it might be a better recommendation than those other two movies. I've seen The Iron Giant, I've seen Frozen. Maybe the recommender found them for me, maybe my friend told me about them. Somehow or another I heard about them, I watched them, and I liked them. If I haven't heard of Zootopia, then the recommender finding it for me is exactly what we want the recommender to do, at least in most consumer settings. So the recommender gets penalized for doing exactly what we want it to do. We probably don't want that. That's the big challenge here. Supposing we had a fantastic recommender that could reliably find these good items that I don't have in my data set, we're not going to find that it is effective when we're doing our standard offline evaluations. So how do we fix this? One way, so in the late 50s, Theodore Sturgeon, a sci-fi author, wrote, 90% of everything is crud. This was refined a couple of years later by Miller. Only 1% is really good. So, we can assume that most items are bad. If we know nothing else about Zootopia, we can assume that it's bad. So this gets us to Sturgeon's decoys, what's called in the recommender systems literature the 1+ random protocol, or its generalization that I've been calling random decoys. Most items are not relevant, so if we select that decoy set to be a random subset of the item universe, instead of everything the user hasn't rated, then those known relevant items are probably not in the decoy set, so we probably won't even be considering them for recommendation. That's the goal. So, we want to find out how many decoys to use. That's the origin story of this work. We wanted to, like, this looks promising, let's go figure out how many decoys we should use. Corin used the method, used 1,000 decoys, but said we really don't know how many. Open problem. So, unfortunately it gets bad. So, in order to reason about this, we wanted to model, we need to model goodness, the goodness rate. What fraction of items are good? And we're doing this right now in a user-independent way. Figuring out what a personalized version of this is future work. But we want the probability of having a random decoy be a good item be less than alpha. Or the probability of no misclassified decoys being greater than, or being at least 1 minus alpha. So, if we assume that goodness of items is independent, we run through the math, what we get is to achieve alpha 0.05 with 1,000 random decoys, only 1 in 10,000 items is allowed to be relevant. Movie lens users rate 10s to hundreds out of 25,000 movies, so that assumption is false. If we go down to 100 decoys, then we can allow 1 in 1,000, which is still pretty high. So we've got, or pretty low. So we really need to make some fairly unreasonable assumptions about the distribution of good items in the set in order to make this method effective, at least with sets such as movie lens. So why are we being so strict? Why are we saying that statistically we want none of these good items in the decoy set? Why can't we just have like 1 or 2, it doesn't matter? Well, if the decoy set contains even one item, even one good item that the user doesn't know about, then in recommender systems for discovery, we want the recommender to find that item. The best recommender will find that item. And so if our evaluation is set up so that the best recommender can never win, then we kind of have a problem. Also, if there are no unknown good items, why are we recommending? At least in a discovery setting. There's still recommendations to do to help users figure out which thing they want now, but we don't need to do discovery if the user knows about all of the good items. So the fact that we're recommending in most contexts means we believe these items exist. So, Random items also are, so they're less likely to be relevant, but they're also less likely to be popular. So popularity does an even better job of discriminating from test items from decoy items if we're randomly selecting decoys than it does if we are just using all of the items. So popularity bias can become worse. We probably don't want that. What's next? What I've been going to is whenever I have ratings, I use rank effectiveness just to sidestep this problem, and then trying to work on how do we quantify, are there other ways we can quantify and mitigate the damage? So that's some of the things we're looking at as far as when we think about the way that the recommender interacts with the user experience, what does that have to say about how our evaluation strategies are actually measuring our ability to deliver recommender value to the users? So, next set of things. Recommender response to users. 3 studies that we performed in the context of Movie Lens, which again is this movie recommendation service that publishes data sets. It currently has 4 different data sets, 100K, 1 million, 10 million, 20 million ratings. The offline things here were all done on 10 million ratings. The 20 million data set didn't exist yet. So the first of these studies is an offline study that looks at the issue of when recommenders make mistakes. And we wanted to see, do different recommendation algorithms make different mistakes? How often? And do different algorithms perform better for different users? And so we counted mispredictions. We used the recommender as a rating predictor. Rather than computing the RMSE, we counted how many times it was more than a half a star off. And we then if we looked at, for each user, we looked at the RMSE, and we looked at the fraction of predictions that they got correct. While the overall average of these resulted in the best, same algorithm performing the best across the board, for an individual user, they only agreed 32% of the time. So giving a very different picture. Which one's right? Open question, but they're giving a very different picture about the recommender performance. And then we also looked at, so if we take one recommender, and it's got, so we take the best recommender, the one that gets the most predictions right, okay? In the set we tested, that was the item recommender, it got 53% of the predictions right. We then say, okay, of the predictions it got wrong, which of the other algorithms got the most of those right? So we get this marginal correct predictions thing. Turns out it was our user algorithm. If we rank these algorithms by RMSE, user was basically the worst, followed only by the mean. But FunkSVD was the second, FunkSVD was slightly better by RMSE, and it was the second best by these percent of predictions correct. But what it was doing is it's making the mistakes in basically the same places as item. So it's not, if we're going to try to put them together, we're just going to see they're making the mistakes in the same places. So we found that the algorithms are making different mistakes. This affects our picture of how they're performing for each user, and there's room to pick up additional signal. We found at least 16% of the predictions could have been picked up by one of our other algorithms if we knew which one to use in each situation. Next study is one that I did with, so all 3 of these studies were in conjunction with Group Lens. This study was also in conjunction with Martijn Willemsen at TU Eindhoven. And we wanted to look at, okay, so we see the different algorithms have different accuracies for different users. Let's look at users saying they prefer different algorithms. What are the factors that drive that? How do different common collaborative filtering algorithms fare when we ask users to pick one over the other? So we gave them a test, or we gave them a survey, had 3 research questions. The first is, how do subjective properties of the recommendations affect users' choice of a recommender algorithm? If a user says, this recommender produces more diverse results than this other recommender, are they more likely to want it to be their recommender? Question 2 was, what differences do users perceive in the output of different algorithms? And then, do we have objective metrics that can predict these subjective perceived characteristics? So we assigned each user 2 algorithms, and we asked them comparative questions. The first one was an initial, which algorithm do you like better? Much more A than B to much more B than A on a 5-point scale. The next were 22 questions on various dimensions of the recommendations, such as diversity, novelty, the extent to which they thought the recommender understood their needs. And then we had a forced choice question at the end. Which one do you want to use? And you had to pick one or the other. We rolled it out in this experiment, in this thing, so they would see the two lists. They could click on a movie and see some more details about it, and they had to answer the questions. There are a couple of interesting features of this experiment. First, it uses joint evaluations. We asked users to compare two lists, rather than often when we're doing a user study on round recommender systems, we just give a user a list of recommendations and ask them just agree, disagree on a Likert scale with statements about that. When we're doing joint evaluations psychologically, that allows people to pick up finer grained distinctions. And we were wanting to be able to find fairly fine grained distinctions, differences in diversity or novelty. The second is we use factor analysis. So we had these 22 questions. They were targeted at 5 different factors. And then we use a structural equation model to test relationships between the factors. This created a new interesting problem. Structural equation modeling is not done on joint evaluation very often. It gets worse when you have a part where you have an incomplete block design like we do. I really like this study, and I'm very pleased with the results. Do not go try to use our experimental method unless you love pain. So we have a hypothesized model and this comes from the psychological theory, where accuracy, novelty, diversity feed into the user's satisfaction. The accuracy also feeds into the degree they believe the recommender understands them. And all of these feed into choice. So the user is going to pick the recommender they're most satisfied with. So we ran the experiment. We had 582 users. And we had them divided between our 3 conditions. The immediate thing we see just looking at which user picked which algorithm, user loses. If the user got user, they were quite likely to not want it. They were pretty much split between item-based collaborative filtering and matrix factorization. We trained this structural equation model on the data. If you haven't seen a structural equation model before, you can think of it as a multi-level linear regression, where each node is a linear regression of its inputs. The arrows, the directionality on those arrows comes from the underlying psychological theory. If the arrows bother you, just ignore them and pretend we're talking about correlations. None of the major results change. Now also, accuracy and understands me disappeared. And the reason they disappeared is they were so highly correlated with satisfaction we could not consider them to be measuring distinct concepts. And so we just dropped them and said, hey, we'll just measure satisfaction. So, first, choice relationship on choice's dependency on satisfaction. The users were more likely to pick the algorithm they found they expressed more satisfaction in. We would hope that this is true, but that is indeed what users did. And that happened both in their initial first impression and then the final choice of algorithm. Diversity positively affected user satisfaction. And then novelty hurt satisfaction quite a bit. If there were too many novel recommendations, users did not like the recommendation list. You have to be careful with novelty. On the one hand, we want to help users find things they don't want. On the other hand, when they're evaluating a recommender and we give them too much novelty, they'll say, what is this garbage? I'm going elsewhere. And so novelty though was positively correlated with diversity. Also, novelty had an additional direct negative impact on first impression. So in addition to negatively influencing satisfaction, it also negatively influenced impression beyond the effect of its negative influence on satisfaction. So that first impression, which list do you like better, was really strongly negatively impacted by novelty. So novelty boosts diversity but hurts algorithm impression. The negative impact of novelty does seem, it's difficult to compare the total effects because the last question is forced choice, but it seems that what's happened, but the direct effect of novelty is not there on the final choice. Yeah.
How did you, maybe this is question, but how did you measure novelty in this case? What was your...
We had 4 or 5 questions that asked users things like this: which list has more movies that are unfamiliar to you? Those kinds of questions. The full list of questions is in the paper.
Okay, so maybe something they already know but they haven't seen yet, that would not be novel.
That would not be novel, correct, yeah.
And diversity is that?
An additional set of, so all these are based on, on the questions. Diversity is questions like which list has a more varied selection of movies.
Okay.
And for each concept we had 4 or 5 questions. You usually use 4 or 5. Factor analysis requires 3 questions for the math to work. So we include 4 or 5 so we can afford to have one not work. And the math gives us a factor loading for each question. And so we drop questions that have low loadings because they're noise. But yeah, so we have 4 or 5 questions for each one. Like I said, the full list is in the paper. And the paper is also, there's a PDF that's on my website. But yeah, diversity had a positive impact on satisfaction. And, but also, interestingly, diversity does not trade off with perceived accuracy. So often in the recommender systems literature, looking at diversity, we talk about the diversity-accuracy trade-off. When we're in user perception land, there is no such trade-off, at least in this data set. This has been seen in a number of other experiments as well, which suggests to me that when we're trading off diversity and accuracy, what we're doing is we're trading off parts of one or both of those metrics that have stopped measuring user-perceived diversity or accuracy.
Just maybe
Yeah.
add something with regards to diversity. I think also it depends on the domain. Like diversity for the movies, I think also like based on the genre of the movies or something like that. So what's the perceived diversity of the users, but for the genre of the movies or something. So in every domain, it's defined differently.
Thank you.
Yeah. So we then looked at the algorithm differences. This is where things got wild for the analysis. So we had the case was which pair of algorithms did you get? The result was difference and difference effects or difference and difference and difference effects. Those are very, very hard to interpret. So we reinterpreted the experiment as if we had run 3 within subject studies. Each one picks a baseline algorithm and then compares 2 other algorithms using the baseline. We found that user was more novel than either SVD or item item, much more novel. User was also more diverse than SVD. The excessive novelty of user decreases just a little bit for users with many ratings. And again, users chose SVD and item in equal measure. We compared these results with the original response to question distributions just to make sure we weren't, to further test the validity of our reanalysis, and they were consistent. So then the objective properties, we measured RMSE for the recommender accuracy over the 5 ratings the user had given prior to entering the study. We looked at the obscurity, basically the inverse of novelty for the recommender, the inverse of popularity for the recommendation novelty, and then we looked at interlist similarity for a measure of diversity. All of these correlated with the subjective properties the direction we expected. Further, their effect in the overall model was mediated entirely through their correlation with the subjective property. So the similarity ratio correlates with diversity. It has no statistically significant effects on any other part of the model. So the subjective, its only link with the rest of the model is its correlation with user perceived diversity. So novelty is a complex story, largely negative effect. Exact use case is going to matter quite a bit though. These results are basically in the setting of the user evaluating a recommender to decide whether they want it. You're going to have different results when the user is interacting with the recommender on a daily basis. We also find that the accuracy novelty trade-off is not showing up when we're looking at user perceived subjective data. So in order to get to the new stuff, I'm going to skip fairly quickly over this giving users control paper. Basically, we gave users a little switch to let them pick algorithms, and we saw what they did with it. A quarter of the users switched. Most of the users left it alone, but a quarter of them went and switched algorithms at least once. But they didn't use the control very much. So they just switched less than 5 times. Most users only switched in one session using the application. They're like, yeah, play with it, and then they leave it alone. They did settle. More of them settled on SVD. Item came in next. We had dropped user from this because it was slow. Very slow. And then the other two algorithms that are less personalized didn't get as many users. So we have 3 studies that find different users preferring different algorithms. We have yet to find a good way to predict whether a user is going to prefer item over SVD. It's possible that it's just noise. But we are finding different algorithms have in offline setting, in user perception setting, in user actually taking action setting, they have different responses from different users are going to settle on different ones. So that's what we've done with understanding the recommended response to individual users. Where are we going next? And thinking again about who all is affected by recommendations is the big thing I'm trying to think about over the next few years. And how do we understand the impact? So one piece of thinking about this is looking at whose need, even just within the users, whose needs are being met. So there's a very nice study that I like from Microsoft Research, Marotra et al. 2017 is the archival version of the paper. They did a study in Bing where they looked at users by demographic instead of overall. And they looked at the search satisfaction being achieved for each demographic group. And this let them ask whether Bing was meeting the information needs of different groups to a similar degree. Because if you just average over all of your users, that's going to be dominated by the largest group of users. And if you're not serving the needs of some smaller group of users, you might not notice it. They might get drowned out in the statistics. So it let them ask separately, are we meeting the needs of 25 to 40-year-old men? Are we meeting the needs of 70 to 80-year-old women? And they could test, this then gives them the statistical machinery to test whether a proposed change to the search engine is how it's going to affect the experience of each of these different groups, rather than just looking at the overall metric. I think this is a huge step forward in understanding whose information needs we're meeting when we build these kinds of systems. There's also limits on behavioral observation when we're seeing what users do. In his 2014 RecSys keynote, Neil Hunt from Netflix made a comment that stuck with me ever since, that the metrics they have can't tell the difference between an enriched life and addiction. They both look like watching movies. And so if we want our recommenders to help enrich users' lives, we need to figure that out. It might mean going and learning, listening to the users, but we also have the challenge, we listen to what a user says, we see what they do. What happens when those disagree? And this isn't an argument for just throwing out our behavioral studies and just listening to users and ruling by user voice mob rule. That's a bad product design strategy. But we need to think about how we can have a three-legged stool where our recommender design involves expert design sense, it involves behavioral data, and it involves user voices, or voices from as many stakeholders as possible. There's also a huge opportunity for recommenders if we understand the user's goals, where the user wants to go, what they like, and we understand their behavior, the recommender might help them bridge the gap, because it's possible that the gap, if the user says one thing and does another, there's at least two possibilities. One, they don't really know what they want. Two, they're not satisfied with their behavior. There's a huge potential here for recommender systems to help bridge that gap. Because we can look at the behavior to see what they're likely to do, and we can find the baby step that's going to get them one step closer to their goal, or their doctor's goal. And then broadening the lens, moving beyond individual users to looking at the user group as a whole and the society in which they're embedded. And so how does recommenders affect users in relation to other users? And how does this interact with the broader socio-technical context, particularly around questions such as biases in input data, assumptions that we make in design and evaluation, and the legal and ethical implications of outputs. There aren't quite as many legal implications when we're recommending movies, but when we're recommending neighborhoods to police, there start to become a lot more of those concerns. So one of the things I'm thinking about is, what does it mean for a recommendation to be fair? The community is in very early stages of addressing this question. But fairness in machine learning has been gaining a fair amount of traction over the last few years. And figuring out what a lot of those questions are being asked in more kind of classical discrimination relevant settings, such as classification used for credit decisions, policing decisions, etc. But what are the fairness constraints or the fairness considerations of recommendation? What does it mean for a recommender to be fair or to be unfair? And can or should we build notions of fairness into a recommender's logic? So for an example of how things can go wrong, a story that was running around Twitter a few weeks ago, Rob Spear was doing some work on restaurant recommendation, and he took Word2Vec and was using it for sentiment analysis and looking at sentiment and user reviews of restaurants. And he looked at the output of his recommender, and Mexican restaurants were showing up lower in the search results. Well, it turned out that Word2Vec, being trained on a bunch of text written on the internet, due to the state of political discourse in the United States, had picked up an association between the word Mexican and the word illegal. And illegal is bad, so therefore Mexican must be some kind of bad. And so it would take the word Mexican describing a restaurant as an indication that the restaurant was bad and reduce its recommendation rank. They caught this problem before ever putting this recommender into production, I believe. But it's the kind of thing that can show up if we're not careful about where our data is coming from, where our algorithm, and what assumptions our algorithms are making, and how we're evaluating their effectiveness and their fairness. So, questions I'm currently looking at are focused on book recommendation right now, looking at the genders of authors. How does the recommender interact with gender distribution of authors in book recommendation? So the question one, is there gender bias in users' rating behavior? Question two, what does the recommender do with it? And is there bias in the input? Is there bias in the output? And are those two biases related to each other? We took book crossing rating data, correlated it with Open Library, did a very stupid thing, ran gender detector over the author names. We need better data than this, but we went with it because it allows us to do a first pass and start getting approximate results that then we can then refine with better methods and better data. And so what we're finding, there's a very mild and very diffuse bias towards men in the male authors in the rating data. There is different algorithms have different levels of bias. All of them have a more concentrated bias, have less variance in their bias than the input data did. And then, but the input bias and the output bias, when we look at it at a user by user level, seem to mostly be independent. You can't really regress. Under the algorithms we tried, data set we tried, regressing output bias against input bias gets you nothing. So, future work on that, we need to improve our analysis, better demographic data, more domains, and extend this to deal with the future feedback loop. Just about 3, 4, 5 years of work. So, a lot of work to be done here, but these are some of the things that we're starting to think about. This work can't be done alone. There needs to be, because computer science can do a lot of things, but there's been a lot of thinking about fairness and ethics in other fields, and integrating with those discussions is something that's important to do. At RecSys this year, we're doing a workshop on fairness in recommendation. The last papers just came in a few hours ago. And we're going to be looking at the question of what are socially responsible recommender systems, and I'm very interested to see what perspectives people are bringing to the table on that, because there's a lot of different ways. Each of these stakeholders might have a different notion of what fairness is, or fairness or unfairness might impact them in a different way. And we need to think about what are the different dynamics of fairness or unfairness in a recommender, or other aspects of social responsibility, if we're going to build recommenders that improve the human condition. We also need to think about whose values a recommender is being built for. Our objective functions that we're optimizing our recommenders for are a way of encoding values. Whose values are being considered in the recommendation process? How do we get more voices involved so that more people's values can be involved? And how do we introduce the notion, how can we get the notion of reciprocity into our technology systems, into our recommender systems? This is another idea I get from Ursula Franklin, of how do we make technology so that technology development, technology evaluation in recommender systems and in algorithmic systems in general is a conversation with users and not just this thing we hand down and then we measure. Questions that I do not have answers to yet. So, wrap up the core ideas I'm looking at. How do we evaluate well? How does the recommender impact different users? How do we look at issues like bias? And then thinking about, don't have any research on yet, but thinking about how do we involve users in the design and evaluation process. Thank you. I'd like to also thank my collaborators at the People and Information Research Team, the Texas State students I did some of this work, Group Lens, Martijn Willemsen. The NSF funded the parts of this work that happened under my PhD. That link has the slides as well as citations for all of the papers that I discussed and mentioned. So if you want to go read more details, the details are all at that link. Thank you very much.